Hello all of you. In this lecture we solve some problems based on linear transformation with respect to the corresponding bases, how we can change of the bases and how we represent the matrix of transformation corresponding to different bases. Now first example is that suppose a T from R4 to R3 be a linear transformation given by T of x1, x2, x3, x4 is equals to the matrix of representation as x1 minus 3x2 plus x3 plus 2x4. Second row x1 minus 2x2 plus x3 minus x4. Third row 2x1 minus 5x2 plus x4. Now we have to find out a matrix of representation corresponding to the standard basis of R4, R3 respectively. Okay, so let us consider B naught be the standard basis of R4 and B naught dash be the standard basis of R3. Then the matrix of representation with respect to B naught and B naught dash it is given by. आपण यावेळेस काय करतो हे मॅट्रिक्स ऑफ रिप्रेझेंटेशन टेकिंग वन इलेमेंट इन द बेसिस ऑफ B naught. What are the basis B naught? B naught is the basis of R4, that is 1 0 0 0. Second element 0 1 0 0. Third element 0 0 1 0. Fourth element 0 0 0 1. This is the basis for R4. And what are the B naught dash? B naught dash it is basis for R3, that is 1 0 0 0 1 0 and 0 0 1. Now these are the B naught and B naught dash. Now taking one element in B naught, say 1 0 0, and it can be written as a linear combinations of the basis elements taking its image. What are the image of T of 1 0 0 0? Substitute the value of x1, x2, x3, x4, then we get the column vector x value 1, all remaining 0, that is 1, second position 1, third position 2. Now 1 1 2 can be written as linear combination of B naught dash. So 1 1 2 can be written as 1 into 1 0 0 plus 1 into 0 1 0 plus 2 into 0 0 1. So first coefficient 1 1 2. This can be written as a column wise 1 1 2. On the same way, taking a second element in the B naught, that is 0 1 0 0. Substitute that value in that x1 x2 x3. We get a column vector in first position. Second coefficient x2 is 1, all are the 0, that is coefficient of x2, minus 3 minus 2 minus 5, therefore this is the third. Second one, third position la 1 hai, 0 0 1 0, so third coefficient 1 1 0, x3 is a coefficient 1 1 0. Next fourth position la 1 hai, x4 is a coefficient 2 minus 1 1, so 2 minus 1 1. Therefore this is a standard matrix representation corresponding to basis B naught and B naught dash. So one is this one is representation corresponding to basis B naught and B naught dash. Now we can find the rank of matrix. How we can find the rank of matrix? For finding this rank of this matrix, this is nothing but the rank of linear transformation T. What is the rank of T? By converting the system into row echelon form, we get it has 3 linearly independent rows. So dimension of rank of that linear mapping T, it is 3, and same as dimension of codomain. What is codomain? Codomain it is R3. R3 is a dimension kiti hai 3. Therefore rank of matrix it is same as dimension of R3, that is the linear transformation T. It is surjective linear transformation. It is onto linear transformation. Okay, so T is surjective. Now let us taking an element. Suppose B is a basis, another basis containing element V1, V2, V3, V4. These are the given. Okay, and B naught, B dash be the another basis containing the basis of R3, W1, W2, W3 with the ordered basis of R4 and R3 respectively. Then we define a mapping as under the linear transformation T of Vi, that is elements of this one, it is called as Wi for each I. So in that way T of V1 it is W1, T of V2 W2, T of V3 W3. So what is T of V4? We take or we substitute T of V4 equals to 0. On that information, we have to find a matrix of representation corresponding to basis B to B dash. How we can represent? Taking one element in basis B. What is element? That element 7 3 1 1. Apply on it as linear transformation. What is linear transformation? T. So T of V1, what is T of V1? T of V1, it is W1. So T of V1, it is W1, which is 1 1 0, which can be written as a linear combination of basis B dash. So how can we write down W1 as a linear combination of W1, W2, W3, which is 1 into W1 plus 0 into W2 plus 0 into W3. So first column vector, it is 1 0 0. Second column vector, T of W2, it is W2, which is 0 into W1 plus 1 into W2 plus 0 into W3. Therefore we can write down the second column 0 1 0. Third column, it is T of V3, which is W3, and write down a linear combination 0 into W1 plus 0 into W2 plus 1 into W3. And the last column, T of V4, it is 0, which can be written as 0 into W1, 0 into W2, 0 into W3. Therefore this is matrix of representation corresponding to basis B to B dash. Now these are the matrices representation. Now also we have to prove what are the relationship between these two representation matrices. As we already known that if we change the basis, then the properties of linear transformations are remain same. Now here we observe a composition formula. Now we know that a matrix of representation from basis B to B dash, it is nothing but that T can be written as I composite T. I composite T by the composition formula can be written as a matrix of representation I from B0 dash to B dash into matrix of representation T from B to B0 dash. Then we substitute this relationship, we get a matrix in terms of this product. Now calculate this product, that I appears for the right of the matrix of linear operator T from B0 to B0 dash. It's the identity operator on R4, and the left identity, it is identity operator on R3. So clearly we can represent what is taking one vector B. What is one vector B? First vector, taking first vector in B, that is 7 3 1 1, and write down as a linear combination. What is its image? I is identity operator, I of V1, it is V1. And then we can write down as a matrix of representation I of V1, that is first vector 7 3 1 1, second vector -4 -2 0 -1, third vector and fourth vector as a column vector. And also find the left product, right product. This one is left product and right product, and substitute in the above formula. Therefore this one becomes this product, which is a verification. ह्या एक्झाम्पलमध्ये आपण इथपर्यंत सॉल्व केलं, इट इज इनफ. हा इझियर वे सॉल्व करण्याचा मॅट्रिक्स ऑफ रिप्रेझेंटेशन करस्पॉन्डिंग टू बेसिस बी टू बी डॅश अँड मॅट्रिक्स ऑफ रिप्रेझेंटेशन करस्पॉन्डिंग टू बेसिस बी नॉट टू बी नॉट डॅश. ओके, so consider the another example. In that example we see the next definition, that is T invariant subspaces. Okay, let V be the vector space over K and T be the linear operator on vector space V. Then a subspace W of V is said to be T invariant if T of W it is subset of W. That is, after applying T on that subset W, then that image set it is also a subset of W. So that subset or that subspace is called as T invariant subspace. That is, after applying T on that subspace, it is also a member of that subspace. Then we say that that subspace is T invariant subspace. What are the T invariant subspace? Singleton 0, it is T invariant subspace. Itself as a vector space. Every vector space, it is again a T invariant subspace. since it is also a subset of subspace of V. So these are the example. Now equivalently, if we define a mapping T cap, it is linear operator on W. In this case, T cap is a linear operator on W induced by T. So proving that T invariant subspace, the corresponding mapping, if W is a T invariant subspace, then the corresponding mapping T dash from V by W to V by W, it is given by T dash of V plus W, it is T of V plus W. It is well defined 1 1 as well as on 2. Therefore it is a linear operator. It is linear operator and it is a finite dimensional. It is also here we verify that it is 1 1. So T dash is a linear operator on V by W, and this operator is called as a linear operator induced by T on V by W. So now let us see the next example in the exercise. That is, T be the linear operator on a finite dimensional vector space V over K, and W1 and W2 be the T invariant subspaces of V of dimension M1 and M2, such that vector space can be written as a direct sum of the subspaces W1 and W2. Therefore, if B1, B2 are the order basis of W1 and W2, then the basis B can be written as B1 union B2, which is a basis of vector space V. And let T1 cap and T2 cap be the linear operators on W1 and W2 induced by T. Then we have the matrix of representation T1 cap, that is restriction map, with respect to the basis B1 it is A1, T2 on B2 it is A2, and same for each T1, T2, T3, T4 belongs to Wi. Therefore each Ti of X belongs to Wi, and this subspace it is the linear this subspace it is T invariant subspaces W1 and W2. For that T invariant subspace, we have the matrix of representation. That matrix of T with respect to basis B, it is nothing but this B1 union B2 forms a basis B. So A1 union A2 forms the matrix of representation corresponding to basis B, and this matrix is nothing but diagonal matrix diagonalized with that two matrices. This is M1 cross M1, this is M2 cross M2. And what is the dimension M1 plus M2? It is the dimension of that vector space V. Okay, so on the same time, this is true for two subspaces. It can be hold for a finite number of subspaces. So suppose W can be written as the direct sum of W1, W2, Wk. Then the each T invariant subspace W1, W2, W3 and so on, having the dimension Mi, and Bi be the order basis for Wi, where Bi can be written as the A1 union A2 union A3 union up to Ak, where the T1 of B1 it is A1, T1 of B2 it is A2. Then the matrix of linear transformation T of with respect to basis B can be written as it is a diagonal matrix having diagonal entries are the nothing but the matrix A1, A2, A3 up to Ak, where A1, A2, A3 up to Ak are nothing but the dimension of the vector space. Okay, so this is an important concept. So in the previous example, if we have the two subspaces, say W1 and W2, if 1 minus 1 0 0 1 minus 1 it is basis for W1, and 1 1 1 is a basis for W2, that is the dimension of W1 it is 2, dimension of W2 it is 1. So taking B as a union of basis element, so B is equals to B1 union B2. So it can be written as 1 minus 1 0 0 1 minus 1 1 1 1. It is basis of R3. So using that formula we have a matrix of representation corresponding to, how we can write down this one? It can be written as a diagonal matrix having diagonal entries A1 A2 0 0. What is A1? A1 is this matrix. What is A2? It is 0 matrix. How we can find out A1 and A2? As we already know that in two subspaces case, we have the restricted map T1 on the B1 and find out its corresponding matrix of linear transformation corresponding to basis B1. So here we can find out a matrix of linear transformation corresponding to the basis B1, which is A1, this one. हा बेसिसला अप्लाय केला तर तुम्हाला ही मॅट्रिक्स मिळणार आहे आणि नेक्स्ट बेसिस अप्लाय केला तर तुम्हाला सिंगलटन 0 मिळणार आहे. देअरफॉर दिस इज मॅट्रिक्स ऑफ रिप्रेझेंटेशन करस्पॉन्डिंग टू बेसिस बी. Here it is clearly define the relationship between that matrix of representation. If B naught is the standard basis of R3, then the matrix of representation corresponding to B naught, again we can write down as a formula in terms of B naught, F can be written as F composite I, then it can be written as B naught IB, BFB, BI, B naught. So I is identity operator on R3. So B naught IB taking one element in B, and it can be written as linear combination of elements of B naught. This is first column, second column, third column. On the same way we can find out this vector, this matrix representation, this one is this, and write down its product. We get a matrix of representation corresponding to B naught. It is this one, 1 by 3, 1 minus 1 minus 1, 1 2 minus 1 minus 2 minus 1 2. So this is satisfy the corresponding relationship, and we get a matrix of representation corresponding to basis B, and another matrix of representation corresponding to the standard basis B naught, using the matrix of representation corresponding to standard basis B, using the formula that if B equals to B1 union B2, then the matrix of transformation corresponding to B first can be written as a matrix of transformation corresponding to B1, a matrix of transformation F corresponding to B2, and otherwise 0. So this one is happen using that formula, and we got a matrix of representation corresponding to both the bases. So in the next lecture we studied how we can represent the matrix of transformation, how we can change, how we can apply change of basis formula, how we can find rank, how we can find nullity, what is rank nullity theorem, what is the dimension of rank of T, dimension of kernel of T, and so on. So today we stop here. We discuss some exercise problem in the next lecture.